This is lesson 8.4 in trigonometry, and we'll call it our first video because we'll probably have several. And the name of this is Lavoisier's theorem. And if you want to be real mathematical, the way you pronounced this guy's name is Lavoisier. Okay, I don't know if it's, I guess it is French. Lavoisier. Anyway, let's go and get started with this. What we're going to do in this lesson is learn how to take the root of a number. Alright, so in the last lesson it was called, let's see, the product and quotient theorem. So if we were multiplying complex numbers, there were some formulas that we learned as far as the product theorem. Now what we're going to do is we're going to take the root, or what you're used to hearing is like the square root of a complex number. And here is the theorem, Lavoisier's theorem, as far as taking a root of a complex number or something with an imaginary number in there. And what we've got as far as root is concerned is maybe we're going to take the cubed root, or the fourth root, or the fifth root. So it's not just the square root of a number. So that's why we're saying the root of a number, because we don't know what root we're doing. Sometimes it'll be the square root, but sometimes it'll be the cube, the fourth, the fifth, or whatever. Let's hope it doesn't go beyond that because it gets kind of messy. So anyway, Lavoisier's theorem says that if we have a complex number where we have r, which is our absolute value, times the and then times our argument, or this would be r cis theta, and if n is any real number, so if we have to the nth power, okay, that equals this. So r cis theta to the nth power is going to be r to the nth cis to the nth times theta. So what we're saying here is we're going to do the power first, and then we'll go back and finding the roots. I got a little bit of ahead of myself. The power is kind of easy to do, so it's not going to take a whole lot of time. And the way this works is, let's say that we have 1 plus I to the cubed root of 3, and we want to take that to the 8th power. Now we can use the FOIL and do it a whole gob of times and end up getting our I plus I to the square root of 3 in a power form. But let's just use Lavoisier's. Now notice, it has to be written in trig form. We can't do it in our rectangular form that we have there. So first of all, we're going to change this to the trig form. Now if you go back to 8.2, it will tell you the first thing we do is we graph it. We go over 1 and up square root of 3. So over 1 up square root of 3. And if you remember from your handy dandy, oops, that didn't look like a 3, does it? That this is going to be 2 because that's a 60-degree angle. We know that just because of our everyday angles. You should have learned that. Okay, so let's go ahead and write that in trig form. And if you remember, it's going to be, we find our r value, and our r is going to be the square root of x squared plus y squared. In this particular case, it's going to be the square root of 1 squared plus square root of 3 squared, which is going to be the square root of 4, which is 2. So our r value is 2. Then we have to find theta. Theta, if you remember, is going to be the tangent of theta equals y over x, which is the square root of 3, over 1, which is the square root of 3. So that's our theta, is the square root of 3. Or that's our tangent of theta, is the square root of 3. And if you take your handy dandy calculator and take the tangent of -1 of the square root of 3, you'll get theta, which you'll find is 60 degrees. Now I went really fast because this is all old stuff. So I found r is 2, and I found theta is 60 degrees. And those are the two bits of information that I need here. So I can get rid of everything else here. Now I can write it in trig form. So we'll write it in trig form in blue here. So it's the r cis 60 degrees. Okay, and we are taking that to the 8th power. So there it is in trig form. I'm going to move everything up, get it out of our way here, so we have a little bit more room than just what I've got there on the very bottom. Alright, so I wonder if there's a way I can move that de Moivre's theorem closer. Okay, so I was able to move that de Moivre's theorem to the front there and put everything else behind it. Alright, so let's go ahead and stretch this to 2 cosine of 60 plus I sine of 60, just so we have it split up there. And what we're doing is we're taking that to the 8th power. Now, according to our theorem here, I'm going to quit saying de Moivre because that's too hard on my face. We're going to take 2, our r, to the 8th power. That's what it says that we do right here. And then we're going to write it as cosine n theta. Our n is that 8 right there. Cosine of 8 times 60 plus I sine 8 times 60. Okay, so 2 to the 8th power is 256. Using your calculator, cosine of 480 plus I sine of 480, and we get that. Now, if you recall, a coterminal angle to 480 is 360. 480 minus 360 is 120, so we're going to change that. Our angle should always be less than 360. So you just subtract 360 from whatever, and you get your angle that's less than 360. So I get that. Okay, so let's move this up. In fact, let's kind of move everything up. I'm done with the theorem there, so I can just leave it where I'm at. Alright, so now what I need to do is I need to convert this back into rectangular form, because the example said express the result in rectangular form. So now I have to take my answer and move it back into rectangular form. So section 2.2 explains how to do that. I guess I should say 8.2. Example 2 in 8.2 shows you how to do that. So remember, we take our cosine of 120, which you know is going to be in this quadrant, and it's going to be a 60-degree angle. So I have 256. Cosine of 120 is going to be in the second quadrant, all students, so it's going to be negative. It's going to be negative 1/2. And then we're going to take our I, and then we're going to take the sine of 120, which is also all students, so it's going to be positive in the second quadrant. It's going to be the square root of 3 over 2, because cosine is going to be your negative 1 over your hypotenuse, and your sine is going to be your opposite, which was the square root of 3 over 2, which is your hypotenuse. They're both positive there, and you're going to get this here. Then we go ahead and distribute negative 128, so that times that divided by 2 plus 128i square root of 3, because when we take 128 times this, or 256, sorry, times this, we cancel and we get 128, just like we did over here. So we get that for our answer in rectangular form. Okay, so that's how you take it to a power. Not too terribly difficult. Alright, sorry to say that the roots of complex numbers are not that easy. So we'll do a couple of those and see if we can get the hang of it. But don't forget to use top of page 353, de Moivre's theorem, in order to take the power of any real number. And when you look at the homework, it will be numbers 1 through 12 are using this particular theorem. Okay. Now when we get to 13 through 24, we're taking the cube roots. And it says graph each cube root. I'm not worried about that. Just be able to find the cube roots. And that's all we're doing in that particular lesson there. I think I might give you a few 31 to 41 to just experiment with, but other than that, we're mostly focusing on 1 to 24. Okay, next video, and we'll show how to take the roots, like the square roots, the cubed roots, whatever, of a complex number. So that's it for 8.4a.